that will implement it in 4 iterations. At the end, I will answer your questions. Here are our main requirements. We have source databases with business data we need to extract and rows that can be sorted from older to newer. After undergoing trivial transformation, we need to load data into target databases. Typical solution for such problem is to build ETL process. On top of that, we'll add additional realistic requirements. It shall be trivial to process a table of a few billion records over the weekend. All network and database failure should be handled gracefully and data should remain consistent. Process should be able to run at arbitrary frequency from month to sub-minute. It should be simple to add more tables to process. Solution should be able to handle processing hundreds of tables simultaneously, and it should be cheap. Today we'll work with two sets of data. Example 1 has simple insert-only source table with sequential key and a value column. Data should be loaded into target table without any changes. You may encounter similar structures, albeit more fleshed out in audit or even sourcing tables. Example 2 scores a version sequential column and a composite key in source, of which only the latest version for any given key should be loaded. Other columns are here for the volume. Such pattern can be encountered when working with history tables or change data capture techniques. To keep examples simple, all tables will be stored in Postgres. We will use next reference architecture today. First, we set up a scheduler that will send HTTP requests through load balancer to trigger workers. As scheduler, you can choose any ready-to-use solution or write your own. Nice things to have are retries, timeouts, and jitter. Setting up scheduler is outside of the scope of this presentation, and we will trigger workers manually. Workers are auto-skeletized .NET Core applications that executes ETL process and will be our focus today. Workers connected to distributed log that prevents parallel execution of the same process and tracks already processed records. And also workers are connected to all source and target databases to perform ETL. We will start worker implementation by defining some handy interfaces. iExtractor defines extract async, which returns all records from source, starting from given change version. Change version corresponds to key 1 in example 1 and a version column in example 2. iTransformer defines transform, which receives a collection of extracted records, and after trivial transformations and filtering, returns collection ready to be loaded. Loader defines load async, which loads collection into a target table. And log defines 3 methods: try, acquire, log async, which marks a given ETL process as running and returns its latest process change version. Update log, which sets a new change version for given process. And release log, which sets process as idling. Implementations of all 4 interfaces are injected into processor, which handles ETL using process async. Let's visualize process async execution flow. As we are working with remote services, most of the time will be spent on long asynchronous operations. To represent it, I separated vertical axis by await statements. Horizontal axis represents steps we need to perform to execute ETL. General flow looks like this. First, we acquire log and latest process change version. Then extract all records from source, starting from given change version. Transform and load this data, and finally update log with new change version and release it. Let's illustrate how the new log will work. I created a table in ACID compliant database, again, Postgres in our case, with 3 columns: process key, last process change version, and is running. Acquiring log means setting is running as true. Updating log means setting a new change version. And releasing log means setting is running as false. So can't be simpler. Let's switch to Visual Studio and see how it looks in code. I started worker implementation by creating a minimal API ASP.NET Core application. And in program CS, I start service collection registrations by adding connections to log, source, and target databases, and also registering some common classes required for ETL. Next registration is more interesting. I mentioned that I want to make adding new processes simple. And to achieve this, I created Fluent Builder that allows us to specify extract and load model, process key, implementations for extractor, transformer, and loader, change version selector, and finally register everything in service collection. Finally, I added 3 utility endpoints to reset log, prepare database and seed some random data, and check database stats, and one endpoint to actually execute ETL. In this endpoint, we use service provider to acquire correct processor implementation based on process key passed as route parameter, and then execute process. Let's look closer. First of all, you may notice that processor does not reference any concrete implementations or types and can be reused across multiple processes. In process async, we start by acquiring log and latest process change version, extracting all data from source, transforming it, loading it, then update log, and release log. Quite simple. Next, let's look at the implementations of these interfaces for example one. First of all, let's look at the log. Log uses Dapper to execute commands to manipulate log table. Main thing I have to emphasize here is you should be very careful with concurrency and performance of distributed log. Ideally, each operation should happen within a single SQL command with sufficient but not overly strict transaction isolation level. Next, let's look at the extract and load model for example one. They're identical in our case and have property names the same as they're defined in tables. In extractor, I use Dapper again to execute a select query and get all records starting from given change version. In transformer, I use link to map extract models to load models. And in loader, I again use Dapper to execute insert on conflict do update command and pass collection of load models as a parameter. Let's start this worker implementation and see how well does it work. First of all, I will use utility endpoint to prepare database and seed, let's say, 100 records. We can check database stats to ensure that source table indeed has 100 records, target table has no records, and log table has one row for example 1 with latest process change version of 0. Next, we can execute ETL process for example 1. As you can see, it finished almost instantaneously. We can check database stats again to ensure that data appeared in target table and latest process change version updated in log. All right, 100 records is not a lot. Let's try a bit more. For example, 10,000 records. We can check database stats again to ensure that there is indeed 10,000 records in the source table. Let's try executing this process again, this time with 10,000 records. And we can see that it takes a bit of time and logs for the Postgres client offer us a hint why it takes so long. Let's wait for it to finish. Oh, 26 seconds. Let's return to the presentation. So, as we demonstrated, inserting even measly 10 key records is unbearably slow because each row is inserted with separate SQL statement. And even if we overcome this issue, synchronizing billions of records will require from dozens of gigabytes to terabytes of memory because we are reading everything in one go. And on top of that, any failure during processing will cost us a lot of work because we update log only after we finish. First, let's address memory constraints. Extractor now returns async enumerable instead of collection. The idea is connection to the source will be kept open and processor will extract new chunks of data when needed. This will limit memory consumption while not compromising performance. Next, let's look at the updated process. First, we acquire log and latest process change version. Next, we enumerate async enumerable acquired from extractor until we get enough records for one chunk. Chunk then transformed and loaded, and log is updated. It ensures that even if failure happens during processing of the next chunk, we will not retry from the beginning. After processing all the chunks, we release the log. Finally, we need to discuss how to load data faster. Most databases offer purpose-built API for bulk loading data. Sometimes it allows to insert, update, and delete multiple records and in one go, like bulk API in Elasticsearch. Postgres has copy command, which is a bit more limited, but does the bare minimum we need from it. It allows us to load a lot of data into empty table fast. The general flow then is simple. First, we create a temporary table with a schema similar to target table. Next, we load it with data using bulk operations. And finally, merge temporary table into target table. Let's return to Visual Studio and illustrate these changes. Okay, so what we changed? First of all, processor. In processor, as previously, we start by acquiring clock and latest process change version. Then we get async enumerable from extractor and split it into chunks of 50,000 records. Then on each iteration of for each, we enumerate one chunk, transform it, load it, and update the log. After that, chunk is no longer referenced and can be garbage collected. I also added try finally block. So if failure happens during chunks processing, we still correctly release the log at the end. Next is extractor. Thanks to the power of Dapper, we don't need to change much. We just replaced query async with query unbuffered async, which conveniently returns async enumerable. Loader becomes significantly longer. As discussed, first we create temporary table with schema like target table, execute copy command to initialize binary import, and then load a collection of load models into temporary table, row by row, value by value. Finally, we merge temporary table into target table. Okay, I believe this is all we needed to show. So let's start this worker and see how well does it work compared to previous version. We will prepare the database again with 10,000 records and execute process for example 1. As you can see, it also become almost instantaneous. We can check database stats to ensure that data indeed synchronized. All right, let's try some realistic amount of data, for example, 1 million records. We will see this data into a source table and execute process, for example, 1. After it finishes, we will be able to estimate our throughput. As you can see, we finished a little in 11 seconds, which means that our throughput is a bit less than 100,000 records per second, which is well above our throughput target, which is nice. I will stop this worker and return to the presentation. So you may have noticed that with current implementation, processor does not start processing the next chunk until the previous one is finished. It may waste a lot of time in some circumstances. It is also time to add process for example 2. We will take existing extractor, transformer, and loader and make them somewhat reusable. Let's look at the optimized process. As you can see, when chunk 1 is transforming and loading, we can already start extracting chunk 2. It is more memory intensive, but it can achieve higher throughput. Making reusable extractor and transformer is easy, and we will check them in the demo section. Loader is more interesting. Loading process has 3 variables. Target table name, which can be provided by configuration property. A list of columns to copy and merge, which correspond to load model properties, and a list of key columns which we can mark in model using attributes. With this in mind, we can use reflection to deduce columns and key columns, build SQL commands, and write async methods. Let's return to the Visual Studio and illustrate all of this. First of all, in program CS, you may notice that alongside example 2, I added a process, I defined a process for example 2. Let's look at their definitions. First of all, for example 1, I noticed that extract and load model are identical, so I just merged them into single model and now use reusable transformer no transform, which does nothing. For extractor, I now use reusable extractor with extract model as type parameter and select query as configuration property. For loader, I now use also reusable loader with load model as type parameter and target table as configuration property. Also, I increased chunk size. While I still recommend to use around 50,000 as a baseline, sometimes increasing or decreasing chunk size may noticeably improve throughput. You may also notice in model 1 that I use a custom attribute to mark a key column. Let's compare this definition with example 2. As you can see, in example 2, it looks about the same, but we use different type parameters and configuration properties. Also, in example 2, we use custom transformer, which performs the duplication and some minor transformations. Next, let's look at the processor. Processor sadly become a lot less readable, but main thing that changed is that we now start extracting next chunk, loading current chunk, and updating log for previous chunk, and then await them all together, which can save time in some circumstances. Next, let's look at the reusable extractor, which still uses Dapper, but we now pass its type parameter and query from PG extractor. No. Next is loader. In loader, we now start by acquiring reflection data for all properties of load model, specifically property name, whether it is a key, function to get property value from model instance, and database type. We then use this reflection data to create SQL statements and write values into temporary table. I believe this is all we needed to show for this worker. So let's start it and see if it still works and if it works faster. As previously, I will prepare a database with 1 million records. It takes several seconds because we prepare the database for 2 examples. Next, we can check database stats and see that now we have data for source table 2, and also that we added a row into log table for example 2. Let's then execute ETL process for example 1 and compare it with previous implementation. And you may notice that it did not become significantly faster. Explanation is simple. In my home environment, we are mostly network constrained, and because of this, if we read and write data in parallel, it does nothing to improve throughput. Next, let's try to synchronize data, for example, 2, which has more rows and overall looks like more realistic set of data that you can encounter in your production environment. It takes a bit more time. But we are still done in 20 seconds, which means that our throughput is 50,000 records per second, which is still well above our throughput target of 20,000 records, which is great. Now let's try something different. I will reset log, for example, 2. Again, start executing ETL process for it. But while it is running, after several seconds, I will kill the worker. It simulates conditions like system failure, memory exhaustion, or if container with the worker killed unexpectedly, or even, for example, if log table is unavailable. After that, let's restart this worker and see how it affected our log. You can check database stats and see that, for example, 2, latest process change version is updated, which is correct because we don't want to start from the beginning. But log is never released, which is a big problem because now to continue processing, for example, 2, someone have to manually intervene into this log table and update its value. Not good. Let's return to the presentation and address this issue. To handle failure we demonstrated, we can add log expiration date to the log. When the log is expired, we are reasonably certain that the previous log holder failed and the new worker are free to acquire it. To make sure that log is expired due to failure and not due to long running process, we can limit process execution time using request timeouts on scheduler and cancellation token in worker. You can also add execution key if you can't ensure that cancellation token will be handled in time. We have already achieved sufficient throughput with a single process, and it is fine to stop here. But we plan to run many processes simultaneously and stated that we don't want to overpay. This means no wasted CPU cycles. I identified extractor, loader, and example 2 transformer as most likely areas of improvements because they perform non-trivial operations for each row and row value. Then I benchmarked them using benchmark.net and additionally analyzed results with perf. Finally, I came up with alternative implementation approaches and other improvements and compared them with baseline benchmark. Due to time limitations, we will not do benchmarking together, but I included benchmarks in repository. First, let's look at the extractor. I investigated its code a bit and found out that Dapper's query and buffer testing just executes data reader, maps raw values to the model, and yields results. Of course, to handle all edge cases, it can introduce inefficiencies. I tried writing my own async iterator to handle extraction. To top it off, npgscale docs recommends to try higher read buffer size for read-heavy applications. After benchmarking, I found out that my new solution does not improve throughput on my hardware, but offer noticeable decreases in memory allocation and CPU utilization. Transformers are often unique for each process, and their optimization gives worse return on time investment. For example, I decided to explore alternative approach to the duplication using order by and distinct by instead of group by. I also tried to use parallel link. Result shows that the duplication using order by and distinct by is faster, but relies on undocumented behavior of link. Parallel link sometimes is faster, but requires more memory allocations. I decided to keep the basic solution. And last is loader. Reflection is considered slow, and we use it on each row value. Moreover, our call to get value introduced block sync. I would like to compare it with accessing properties and writing columns values directly. Finally, npj-scale-dex recommends to try higher write buffer size connection parameter for write-heavy applications. Again, benchmarks does not show improvement in throughput, but we almost eliminated memory allocations and significantly decreased CPU load. So how can we avoid perils of reflection and libraries, but not write whole lot of code for each process? I see three approaches. First is to write separate .NET applications that will analyze database schema and create classes we need, similar to how scaffolding database schema works in Entity Framework. Alternative is to utilize reflection for initial model analysis, but use compiled expression trees to do actual work. Or this approach is used by Dapper. Or we can use incremental sort generators to analyze model and write code at build time. I decided to use second and third options because they're most interesting and educational. Let's return to the Visual Studio one last time and see our changes. First of all, I updated connection strings and added increased buffer size to source and target connection because it improves throughput and requires minimal effort. Next is updated lock. Lock now takes into account lock expiration when acquiring lock and execution key when updating and releasing lock. In processor, we now propagate request cancellation token and also create execution key at the beginning. So the idea is, for example, if we agree that our lock cancellation time is 10 minutes, we can configure scheduler to cancel requests and retry after 9 minutes. And then this request cancellation will be propagated through cancellation token, execution will be aborted, and lock will be released, which achieves what we wanted. Next, let's look at the extractor. Extract async now become async iterator function that executes data reader, checks if there is any data to read, and then for each row in data reader, it reads it and maps it to extract model and yields result. Let's look at the implementation for map function. To generate it, I decided to use reflection with compiled expression trees approach because it allows access both to reflection data and to column schema from data reader. I start from joining this column schema with reflection data and get some data. Next, I prepare method infos for get methods of data reader. And next, I start to use expressions to define our mapping function. First, we need to instantiate extract model. And then for each column, we get column value from data reader, convert it if needed, assign it to the model property, taking into account possible null values. Here I have to mention that expressions are quite limited in what they can express. For example, they do not support most of the modern C# syntactic sugar, async await statements, or even implicit casts. And sadly, for Microsoft, it's not a priority to improve their capabilities right now. We finish our expression creation by combining all expressions into single expression block and compile it into Lambda function that we cache for the all lifetime of the worker. And lastly, let's look at the loader. It still has recognizable structure, but now everything related to specific process and load model moved to implementation of IPG copier interface. Let's look at the implementation of such interface for example 2. You can see that it contains prepared SQL statements to create, copy, and upsert, and also function to write whole row into a temporary table. But here is the question: where does this implementation comes from? It comes from source generator. To create source generator, I first created separate .NET project that references .NET Standard 2.0 with single class that implements Incremental generator interface. It defines one method initialize where all the magic happens. First of all, I use register post initialization output to emit static files. In our case, it is marker attribute to mark load model, attribute to mark key columns in load model, and also IPG copier interface. Next, I start to define our source generation pipeline, which is executed each time a project is built or code analysis is running, and provides access to changed syntax nodes. Here I have to mention that you should be very careful when defining this source generation pipeline, because it is very easy to make it slow, and if it is slow, it will slow down all your builds and code analysis. Recommended approach is to use for attribute with metadata name, where we can provide our marker attribute, and source generator extremely quickly filters only changes in syntax nodes marked with this attribute. I also use additional predicate to filter only changes in class declarations, in our case, class declaration for load model. And also I use transform to extract data we actually need for source generation. Ideally, output of each step of source generators should be comparable, because if previous execution yields the same result as the current execution, source generator is smart enough to skip all the next steps. Another hint is it provides cancellation token everywhere, and if you do computation-heavy operations, it is a good idea to handle it. Let's look at the transformer closer. Source generators provide us information about changed code in two forms. Syntax model, which with syntactic and lexical info, this basically describes what is written, and semantic model, which explain what does the syntax means within current context. And also for attribute with metadata, give prepared data about marker attribute. We use all this info to get target table name, inspect all load model properties to get their names, whether they're a key, their types, and also to get load model class name and namespace. This source generator pipeline then put into register source output, where we can actually generate our code using wrapper over string builder. I have to mention that in this example looks quite complex, but I still prioritize its simplicity, and it might be quite brittle if you try to do something more interesting with your load models. So let's start this version of the worker and see if it still works after all our changes. I have to close previous worker before this, and okay, now it should work. All right. As last time, we will prepare database with 1 million records, which will take a few seconds. All right. Next, we will execute process, for example, 1 to ensure that everything still works. After that, we can also execute it, for example, 2, but maybe we'll skip this. As you can see, it is still working. Again, it did not become a lot faster because we're network constrained, but still there is some improvement. So let's reset log for example 1 and experiment and see how well does this implementation handles request cancellation and system failures. First, we will start execution of example 1, wait a couple of seconds, and close the window, which effectively cancels request to the worker and should release the log. For example 2, we will also start execution, but during this execution, we will kill the worker. After that, we'll restart our worker and see how it affected the log. All right. As you can see, for example, 1 change version is updated, which is correct. Log is released, which is correct. Everything is all right. It handles cancellation, request cancellation as we want. For example, 2, when system failure happens, also change version is updated. Log is not released, but it now has log expiration 10 minutes in the future. So after 10 minutes, another worker can continue to process data, for example, 2, which is also what we wanted. So I believe we achieved everything we wanted for our worker and can finish our presentation. I left for you some useful links that include good examples and documentation on source generators, expression trees, and also benchmarking and analyzing results of the benchmarks. And now I'm ready to answer your questions, if there is any.